Mark is director of the Climate Change Institute at ANU. He's also an honorary professor at my alma mater, Melbourne University. He's vice chair of the International Panel on Climate Change. So if you have questions about that and how it works, do throw them Mark's way. He's a member of the Australian National Climate Science Advisory Committee. He's advised the US federal government on climate assessments and contributes to many, many institutions, national and international. He has oodles and oodles of scientific papers to his name on many subjects, but I first met Mark through his expertise and his work on climate change and agriculture. So he's got a special passion for that. He's been doing this for a long time. He's been a major contributor to the IPCC since 1991, and he's contributed to most of the assessment reports. And he shared the 2007 Nobel Peace Prize for the IPCC with IPCC participants and Al Gore. And he's going to give us the big picture. Give it to us.
Okay, I'll try, Corey. But thanks everyone for your time this morning. And what I'm going to do here is cover what is actually an enormous topic in a relatively short period of time. And so it will be, in a sense, a bit of a skate through of the topics. Now, just checking, you can see a full screen picture. Okay, all good. So just what I'm covering today is to some extent the fundamentals of the climate system and climate changes, and particularly looking at the sort of extremes, because they're often what impact most on agriculture. The picture there is just a bit of a question, you know, like, are we able to get a bit of a smooth ride somewhere? And the ambiguity there is that looking out the back window, or is that looking out the front windscreen? And that's what I'll be trying to illustrate in this presentation, that we're already having a change in climate, and future changes even more significant. So the fundamentals of human-induced climate change, because there has over the history of Earth been natural periods of climate change, of course, is that we're producing huge amounts of greenhouse gases. And this is just the carbon dioxide trace going back to 1990 in billions of tonnes per year. And this is just from fossil fuels and cement manufacture, things like that. And you can see back in 1990, we're around about 22 billion tonnes. We're currently about 37 billion tonnes, and that's been going up quite significantly. And you can see that exponential growth period, particularly from around about year 2000 to 2015, was particularly associated with development of places like China and other countries in transition. Importantly, you can see the little dip around the global financial crisis period, 2008, 2009, and you know that threw a lot of economic sort of waves through the system, but in terms of greenhouse gas emissions, made almost no difference at all. And over recent years, last year, greenhouse gas emissions went up about 0.6%. The year before that went up about 3%. But the question is, what's going to happen this year? And so we're probably going to drop our emissions by about 7%. And that's what it looks like on that graph. You know, it's not an insignificant number, but it's actually relatively minor. And the problem in terms of greenhouse gases is that decreases like this, whilst they're positive, make very, very little difference in terms of the overall picture of increases of greenhouse gases in the atmosphere. And that's because for every tonne of these billions of tonnes of greenhouse gases, roughly speaking, a quarter of it gets absorbed by the ocean, a quarter of it gets absorbed by the land, the ocean, the trees and the shrubs and the grass, the soil, and half of it, roughly, accumulates in the atmosphere. And because carbon dioxide lasts for a couple of hundred years or more in the atmosphere, it just essentially builds up and up and up. And so to solve the climate change problem, it's not even about reducing it to, you know, half or anything. It actually has to take it back close to zero, because that's the only way we can stop that accumulation in the atmosphere. And And what this might look like in the future is, I don't know the answer, but if we keep on going as we have in the past, sort of bounce back, you know, the snapback sort of idea that politicians were talking about at the start of the global financial crisis, this is what it might look like. If we go into a green recovery, this is what it might look like. But the really important thing is that if we're to actually keep temperatures down to 1.5 degrees, we have to keep on doing 7% every year for the next couple of decades. And so we actually have to go on this trajectory, and I'll show this, a bigger picture of this later. We have to keep on reducing greenhouse gas emissions at roughly the same rate that we have in the last year during the lockdown. And that's a really scary thought for a lot of people, because you know the pain and suffering associated with the lockdown and those reductions in emissions is really substantial. But the really important point there is none of that was actually designed to reduce emissions in a relatively painless way. And in fact, we know how we can reduce our greenhouse gas emissions and maintain economic growth and activity. And so the challenge is for us to start making good policy decisions rather than default policy decisions. So given that we've been producing lots of greenhouse gases, what does that look like in a long-term picture? So this is a graph which covers carbon dioxide concentrations in the atmosphere going back almost 1 million years, so 800,000 years. And you can see that it's gone up and gone down over that close to 1 million years. And if we look at what's happened to the Earth in that time frame, when we have those dips in the concentration of carbon dioxide, that's when we get ice ages. When we have the little rises in the concentration, that's when we get the interglacials, the warm periods in Earth's history, which we're in at the moment, fortunately. And but you can see over that almost 1 million years, over multiple glaciations and interglaciations, so that's across different glacial cycles, we can see that there's a top and a bottom of carbon dioxide concentrations. That is, left to its own devices, the Earth system will modulate or moderate the changes in carbon dioxide. So it limits the top and it limits the bottom. And so it bounces around between about 180 and 280 parts per million. Right now, we're sitting at around 415 parts per million. So we're way outside the historical envelope of variation. And this graph indicates that if we go to a high emission scenario, which is roughly the emission scenario we're on now, we'll head towards 900 parts per million. And so you can see from this graph that, that we're way outside the natural variation. So if anyone says to you something like, oh, it's all happened before, you know, it's all part of a natural cycle, well, that's just completely wrong. This is not happened before. In the history of humankind, so humans have been around about between 140 and 280,000 years as a species. This has not happened before in human history. This has not happened in the last couple of million years, if you extend this record back a bit further. This is entirely unusual and it's entirely driven by humans. And we've known for 150 years or so that if we pump greenhouse gases like carbon dioxide into the atmosphere, we'll warm the Earth. So this is not new science. It was first hypothesized in the 1840s. It was first measured in the 1850s. It was first modeled in the 1890s. And everything about the science of this that it's accumulated just reinforces the fact that if we put greenhouse gases in the atmosphere, it'll warm the Earth. And the extent of this warming, I think it's illustrated in this particular animation, which I've got here, which is put together by a guy in Finland, Antti Lipponen. And I'll just explain this before I run the animation. And so what we have is we have temperatures from a huge number of locations across the Earth. So every little dot down here, the coloured dots down the bottom, is a different location on Earth. And they're arrayed in different years. So this first one was for the 1990s, and then it will step through year by year up to the current. And so what you can see is there's the equator, the dark line in the middle of those coloured dots. Downwards is towards the South Pole, upwards is towards the North Pole. And the colours of the dots relate to the temperature in that particular location in that particular year. So if it's blue, it was colder than the long-term average. If it's red, it was hotter than the long-term average. And the curve at the top is just the sum of all of those little dots down the bottom. So it gives the global picture. And you can see that in the year 1900, there was, roughly speaking, the temperature range went from about 2 degrees below the long-term average to about 1 and a bit degrees above the long-term average. So the difference between the coldest place on Earth and the hottest place on Earth was a bit more than 3 degrees, the difference between -2 and +1. So what I'll show you is this animation, and you can see just how radically things have changed in that time frame due to human influence. So I'll just run that. And so that's up to close to the present. And what you can see there is, of course, that on average, the temperatures increased across the globe. But the really important story here is not about the average temperature increase. It's actually about the temperature variation. And if you remember, going back to 1900, is that temperature range was essentially 3 degrees. Now we're getting some places which are still 2 degrees or maybe even 3 degrees colder than the long-term average. But some places are getting 5 degrees or more hotter than the long-term average. So that range between those is now around about 7 or maybe even 8 degrees, going up from around about 3 degrees 100 and a bit years ago. And so that is about risk. That's about climate risk. We are getting now conditions which are simply extraordinary compared with the long-term record and the long-term averages. And it's that extreme, the changes in the temperature extremes, which I actually think is the big story and which a lot of people miss because they focus instead on the averages. And as we know, it's the extremes which impact on agriculture. Now, if we look at Australia, Australia's story is basically the same, is that this is just a graph straight from the Bureau of Met website showing temperatures across Australia going back to 1910 or so. And you can see that those temperatures have increased and increased quite radically. And last year was by far the hottest year on record, 1.52 above the Bureau's baseline. So the Bureau has a baseline of 1960 to 1990. So it's a very recent baseline. If you take this back to be more associated with the pre-industrial baseline, we have to add about another 0.4 degrees on that. So in terms of, say, the Paris Agreement, that sort of temperature metric last year, we were sitting around about 1.9 degrees above the pre-industrial. And last year we had the hottest summer. We had heat waves in several months right across the year. So from the start of the year through to the end, and we had the hottest day on record, and that was beaten on 2 successive days. So the first of those, I think the previous one was 40.2 degrees. It went up to 40.9 degrees averaged across Australia. The following day, it went to 41.9, and the third day, it almost broke that new record set only the previous day. So we almost had 3 days in a row of record-breaking temperatures. And these are just extraordinary, 41.9 degrees averaged across the continent. And those extremes are happening everywhere and pretty much all the time. So this is similarly a graph from the Bureau of Meteorology. And what this shows is the area covered of Australia that has extremely hot conditions. So it's what we call the top decile, the decile 10 temperatures. And on average, you'd expect Australia to have 10% of the area covered by those conditions. But what we've found is over recent years, we've actually got 90% or so of Australia covered by what used to have been thought of as an extremely hot year. And you can see that that graph just keeps on going up and up towards the right. The dark line is the 10-year rolling average. And so the message here is that, yes, the temperature is going up and it's going up everywhere. There is no place you can go on Earth now which is not being affected by global warming. It's global for a reason. But really importantly, that graph that I showed you before that stretched out both the positive side of things and the negative side of things, applies also in Australia. So in parts of Australia, particularly the southeast of Australia, we're seeing increased in frost risk. So even though the average temperature has gone up, we also are getting increased frost risk. So those particularly sharp cold nights, particularly late frosts, are really problematic. And what this shows is it's a graph which tries to sort of really paint out frost risk as it accumulates over decade by decade. So this is sort of a simple version of frost risk for Wagga, this particular location, and for the 1950s. So you can see what this plots out is the temperature. So 2 degrees is a light frost, -2 is a heavy frost, and this is the time date of year. So day 180 is the middle of the year, going up towards Christmas time, day 300. So start of December, and actually November. And we can see this is the sort of picture of frost in the 1950s, and I'll just skip through decade by decade what has happened. So 1950s is 1970s, 1980s, 1990s, and year 2000s. And you can see that the frost risk in this particular location, but many other similar locations around Southeast Australia, has actually increased over decade by decade, even though we've had warming decade by decade. And this is largely driven by the changes in the synoptic systems, the sort of location and intensity of the high pressure systems. And I'll show you what that looks like in a minute. But these changes in those, particularly those pressure systems, which have tended to drive the cold fronts and the rainfall, the winter rainfall bearing cold fronts, instead of coming across the southern third of Australia, they're now being pushed down into the Southern Ocean. And that, plus the changes in tropical rainfall, means that in a sense, our rainfall distributions have changed, as well as the rainfall amounts, which I'll show you in a minute. So this is a graph coming from St David Stevens over in WA, which shows the top left-hand panel is the historical rainfall distributions. So we have a sort of essentially summer-dominated tropical rainfall in the north, winter-dominated in Mediterranean-style rainfall in the west, and also down through the southeast. If we actually look at those sorts of weather patterns that have happened since the turn of the century, so in the last 20 years or so, what we've seen is that the tropics are coming further south, and the dry centre is pushing out towards the coast. And so we've both got more summer-dominated and, on average, less rainfall across the southern parts of Australia. More rainfall in the northwest, but in the southern parts of Australia, on average, less rainfall. And so we've seen these patterns already. So this is looking through the back window before we even get looking forwards. And as a result of these changes in rainfall, we're seeing increased extreme dry periods in Australia. So last year was the driest year on record by far. It had a record positive Indian Ocean dipole. So that was the ocean temperatures off the northwest, which were driving a lot of that dry weather. And on many places, it was the worst drought on record. So that's that bright red color in this graph. So you can see that was incredibly extensive, and it hurt so many people in so many ways. We had towns and rivers running dry. We had the massive fish kills in the Darling River, but also we had record rains and severe floods. And they were particularly associated with the tropical cyclone up in the northwest, and also the northeast. And that one in the northeast, if you remember, because it came on the back of a drought, there was very little feed. So you got a lot of cattle getting cold, because of the rainfall, and they had very little feed, so they starved and they died. So something like 500,000 beef cattle died with that event. And pretty extraordinary if you're thinking about it, that you had a whole bunch of cattle dying in an extremely wet period in summer in Northern Australia. So that's the sort of thing that extreme events really impact on. And if we look at rainfall trends, they're particularly powerful in the southwest of WA, where we've seen a really significant reduction, particularly in winter rainfall. But that's not the only place where that's happening. It's just the strongest signal. If we look at what's already happening as a result in terms of Perth's dams, we see that those Perth's dams, which used to get around about 400 gigalitres inflow each year, they're now lucky to get 30. It's a massive, massive change, like, 85% reduction that's already happened, and there's a strong fingerprint of climate change on this. And in fact, dams which were actually built and designed to store rainwater throughout river flows and creek systems there, now are actually storing desalinated water. So their function has fundamentally changed in how the water that they source to store. So this is happening, and it's happening already. And as I'll show you, the projections are even worse than this. And I mentioned before that a lot of this is happening because of the changes in the pressure systems. So what this graph shows is it's the reduction in the number of high pressure systems that have accumulated. So it's the trend associated with these. And effectively, and I'll just explain. So what we used to have is high pressure systems, say over winter, would be located over roughly the middle of Australia. And now, because of climate change, they're migrating around sort of latitudes of Victoria and Tasmania, often in the middle of winter. So those pressure systems have moved almost half a continent down because of climate change. And that's associated with the temperature gradients that we're seeing, and to some extent, the ozone hole over the Antarctic. But what's happened is, because those high pressure systems are moving down, a couple of things. One is they're driving those rainfall bearing cold fronts, which I mentioned before. They're driving those down instead of coming over at sort of Melbourne to Sydney latitudes and even further north. Now they're coming over sort of Tasmania and Melbourne latitudes. The other part of it is, when you've got these high pressure systems which are migrating at sort of roughly Tasmania type latitudes, the air which is circulating around them, which circulates like this around them, is now going over sort of Macquarie Island latitudes. So it's bringing super cold subpolar air up over southeastern Australia. And that's why we're getting those particularly late killer frosts, when you get a combination of high pressure, which means clear skies, and this super cool air coming in over from the Southern Ocean. And it's, just to reassure you that this is not a random thing that's just happening over Australia as part of a global pattern. So this second graph shows you a polar bird's eye view across the Antarctic. So it's looking downwards across Antarctic. And you see that this change in pressure systems not only affects that Australia, but it's right around the globe, affecting South America and also South Africa. Think to the Cape Town droughts that we saw just a little while back. And so this is part of a global change, and it's driven by climate changes. So what does this mean for what we might think of as the operating envelope for agriculture in Southern Australia? So what I've done here is a really simple thing. I've plotted for each year, so each dot is a different year, and I've plotted that year against rainfall and temperature on this axis. And so this is the picture for the pre-1950s. Each of those dots is simply a year. And we can see that there's actually a strong relationship there. So those years which are hotter are also drier. And those years which are wetter are also colder. And so that line, that straight line, is just simply the trend line, the regression line between those. And you can see that slope of that line is really quite powerful. If we actually then look at the post-1950s and the post-2000 years, we can see that the relationship between temperature and rainfall is robust. Is the slope of that line is consistent across all of those different periods. But when we actually lay these on top of each other, we can actually see what's happened in terms of the operating envelope, that trade-off between temperature and drought and rainfall that occurs in our systems. And you can see the 1950s now almost, there's no overlap with the envelope of conditions we're experiencing since the turn of the century. And within a few years, that envelope will now be completely separated. And in particular, if we look at last year, we can see what an outlier that was compared with anything, say, that our forebears have dealt with. It is just so grossly outside anything that we've had to deal with before in terms of that combination of temperature and rainfall. And this is driven by climate change. And so we need to be very aware of the possibilities of occurrences which are not only like last year, but worse than last year, and how they may be coming down the track. And it's not just that temperature and rainfall, but things are happening to things like our vapor pressure deficit. So the vapor pressure deficit measures the difference between the amount of water that the air can hold at a given temperature versus what it does hold at the given temperature. So it's essentially the dryness of the air. And this is a global study, but what it showed is that the vapor pressure deficit has now increased quite significant and is projected to increase further out into the future. Now, this is really important because vapor pressure drives evaporation. So you lose water from your dams more quickly, but it also reduces the water use efficiency of crops and grasses, so your pasture grasses. So each given amount of water, millimetre of water, will actually grow less crop when you've got a high vapor pressure deficit. So this is an additional concern. And of course, these combination of things, temperature, vapor pressure deficit, and changes in rainfall, drive things like droughts. So this is just from a study a couple of years ago, which looked at trends in drought over the last 50 or 60 years. And you can see that Australia had an increasing trend towards drought in the southwest and the southeast, but we're not the only part of the world to have that. And those sorts of changes in drought and temperature also drive fire risk. And what we've seen, particularly in last summer, was massive increases in fire damage, area burnt, and the duration of the fire season. So when we look at what's happened to fires, that fire season is extended, the intensity and frequency have increased, the days of high fire danger have increased, and the affected area has increased across southern Australia. So fire is an increasing risk. We also see changes in risks such as tropical cyclones, which can impact heavily on agriculture in particularly the northeast and the northwest. And it's not just the sugarcane and bananas that get affected, as we just talked about. It's also things like the beef cattle, which can get affected. But of course, cyclones also drive the water that goes into our central drainage systems, ending up in Lake Eyre, but through the Channel country. So that's cyclones typically are where we get those systems filled up. And if we look globally at cyclone numbers, they're going up. If we look particularly at cyclone wind speeds, it's the really dangerous ones, the category 3, 4, and 5 ones, which are actually going up fastest. So if we look at the category 5 wind speeds, they've gone up almost threefold. So the frequency of those really nasty cyclones has effectively tripled in the last few decades. And it's not just that they're getting more and they're getting stronger, they're also affecting new areas. So there's a poleward migration of cyclones, so they're stretching further towards the South Pole in the Southern Hemisphere and ditto in the Northern Hemisphere. So we're getting places affected by tropical cyclones which simply weren't affected in the past. So that's the sort of the backwards looking part of the talk. And so then I'll just move into the forwards looking part of the talk. But what I've tried to do is give you an understanding of what's already changing in our climate and the linkages to climate change and that, so greenhouse gas emissions, and the processes which are driving those changes. So changes in the high pressure systems, etc. And so then the question is, okay, well, how might that propagate out into the future? So when we actually look at this is greenhouse gas emission trajectories. Again, it's the same graph that I showed up very first time. So it's the fossil fuel and cement components. There's lots of other sources of carbon dioxide and other greenhouse gases like methane and nitrous oxide, which aren't included, but are going on similar expansive trajectories. So the sort of path we're on at the moment will take us up to a world which is possibly 3, 4, 5, or 6 degrees warmer than our historical. And that's essentially the current trajectory we're on at the moment. If all of the countries actually did what they'd say they'd do under the Paris agreements in terms of emission reductions, Australia has a target, say, of 26 to 28% against our 2005 emissions. And other countries have similar sorts of targets, sometimes more stringent, sometimes less so. But if everyone said that what they do under the Paris Agreement, we'd still end up with a world which is about 3 degrees, maybe 3.5 degrees warmer than the historical. And to put that in context, these numbers in context, if you remember that graph that I showed you before, the difference between an ice age and an interglacial, the temperature difference between the cold periods on Earth and the hot periods on Earth is only around about 5 degrees. So when we're talking the current trajectory of temperature changes of possibly up to 5 degrees, that's like an ice age, but in reverse. An ice age has fundamentally changed the face of the Earth. The temperature was down, of course, but we had 2 kilometres of ice over parts of North America and Europe. We had the sea level was 120 metres below what it is currently. So ice ages, you know, that temperature 5 degrees fundamentally changes the face of the Earth. And it would be naive to think that a temperature increase of 5 degrees likewise didn't fundamentally change the face of the Earth. So these might sound like small numbers, but they actually mean big things when it comes to how the Earth operates. So if we're actually to meet the main goal of the Paris Agreement, that's keeping temperatures well below 2 degrees, we have to go onto an emissions trajectory like this. If we're to keep it to 1.5 degrees, we have to go onto emissions trajectory like this, the dashed line. And you can see that they're fundamentally different from where we're going at the moment, the trajectory we're on. Now, some people see this as a really big negative. Some people see this as an opportunity. So depending on what sort of view you have in terms of opportunities, you could actually see, okay, well, if I'm into renewables, if I'm into alternative energy, if I'm into electric vehicles, this is a fantastic opportunity. It's those businesses, particularly things like coal-fired power stations, which see this as a threat. So this is not fundamentally a threat or an opportunity in terms of those emissions. It actually depends entirely on your perspective. There's no absolutes here. It's all about relativities when it comes to those sorts of opportunities. But what does this mean in terms of climate? So pretty fundamental differences. This is graphs coming out of the recent IPCC reports, shows temperature increase at the top 2 bars. That's the daytime temperatures and the nighttime temperatures. That's the left and right columns. Under a low emission scenario, or down the bottom, a high emission scenario. And the bottom is where we're heading, and that gives us potentially temperature increases across parts of the world which are 8, 9 or 10 degrees hotter than the long-term average. And you might say, this is extreme, this is extraordinary, it can't happen, except it actually already has happened. And up in the Arctic, we've already had some years which are 8, 9 and 10 degrees hotter than the long-term average. And in fact, the Svalbard seed vault, which holds all of the world's seed collections, you know, different varieties of wheat and maize, etc. That was put in the deep north of Norway, where it was expected to be iced in forever. And that flooded the other year because they got such high temperatures that it actually melted the ice around them and it flooded the seed vault. And that's already happening at just 1.1 degree of global warming, let alone what we're potentially seeing in the future. So this means huge changes in heat stress impacts across the globe. So this is a study done by Antonio Mora from Hawaii. The top left-hand panel is the frequency of what they call deadly heat stress days. So these are days when the heat and humidity conditions essentially mean that you can't maintain thermal balance if you're outside doing active activities. And the bottom right-hand panel is the scenario for the emissions trajectory we're essentially on towards the end of the century. And you can see that right across the tropics, the equatorial and tropical zones, including Australia, we have a situation where almost every day becomes a heat stress day. And that will affect, their estimate is about 3/4 of the population of the Earth by the end of the century. In Australia, this is work that I did, very similar work, but going back 20 years or so ago, just to illustrate that. So if we look at historical heat stress, the top left-hand panel, Places like the top end used to get around about 70% of days were heat stress days. Places down like Canberra, Melbourne, Perth get less than 10%. Under a 2.7 degrees Celsius scenario of warming, that fundamentally changes. And 2.7 is probably modest in terms of where we're going at the moment with our greenhouse emissions. And we can see that right across the top third of Australia, most days become heat stress days. And those sorts of conditions, which used to be experienced in Rockhampton up here, are now experienced across the bottom third of Australia. And I've lived in Rockhampton and places north and south of Rocky, and I know what it's like, and it's a fundamentally different climate from the one we're used to in southern Australia. And this will impact on people in terms of outdoor operations, it'll impact on livestock, and it will impact on our plant-based systems. So big changes are coming in terms of temperature. If we look at rainfall, so rainfall is a very variable change thing out into the future. So we get some bands of the earth, like around the equator, where rainfall is likely to increase significantly, and up in the Arctic, but bands of the earth, including the southern temperate zones, which covers Australia, and similarly in the northern hemisphere around Europe, around southern Europe, where rainfall is likely to decrease very significantly. And if you wanted to combine those couple of things, temperature, rainfall, into a drought index, there's some recent work which looks at what might happen in Australia over different periods of time. So this is covering what we call just drought conditions and what the authors called extreme drought conditions. And these two panels, the top one covers the percent of time in drought across Australia, and the bottom is the mean drought duration, so how long the droughts go. And what this shows is both in terms of the percent of time and also the duration for different regions within Australia, they're all increasing. So drought is going to become a much more common feature of our landscape. So drought being relative, it's compared with what we used to think of as wet versus dry periods in Australia. And importantly, the extreme droughts are going to increase both in terms of duration and frequency. So, you know, climate change does not bring a lot of good news for Australia. And if we look at one of the components of that, which is what happens to our water systems. So this is, again, an IPCC graph which shows changes in runoff per degree warming. So if we have 2 degrees warming, you multiply these numbers by 2, ditto with 3. And you see in, say, the Murray and southeast, it's about 10% per degree. Over in the southwest, it's 25% per degree. So for example, if in a 3 degree scenario, it means around the Murray would lose about 30% of stream flow on average, and it's worse in the west. But it's really important to understand that these actually may be underestimates of the change. So if we've, for example, the Kielty report recently actually indicated we'd lost probably something like a quarter of rainfall or runoff in the Murray and tributaries due to climate change. And so the scenario we're probably dealing with is probably this one. And this is the worst case scenario under the IPCC, which talks about 20% per degree, and over in the west, 30% per degree. And under this scenario, essentially there's no place in Australia which does not suffer in terms of runoff under climate change. But there is variation from place to place as to how bad it may be, and Tassie being the least, as well as in the northwest. So this is the sort of amount of runoff in our rivers, which feeds our dams and therefore supplies our water for irrigated agriculture, for the environment, for mining, for towns. And the picture is not looking really good there either. And lastly, it's about the risk associated with climate change. So it's the variance of climate conditions. So this is work came out of Scott Power from the Bureau of Meteorology, looking at the variance or the disturbance associated with El Nino and La Nina events. So this year we're luckily in the La Nina, which is part of the reason why we're getting some nice rainfall. But Scott's analysis shows the change in frequency of disruptions associated with El Nino, La Nina over different periods of time. So his assessment is that we've already had a really significant increase in that disruption, and that's going to increase radically if we go on a high emissions scenario where we currently are, and moderately if we go on a low emissions greenhouse gas scenario. And Mark Wooten will be talking about greenhouse gas emissions and agriculture later, so I won't cover that. But what this indicates is that the risk associated with agriculture is likely to increase, and the degree of increase depends in part on what we do in terms of greenhouse gas emissions. And other authors have combined that into sort of global multi-hazard maps, and I won't dwell on this to any great extent because there's a lot of info here, but what they did was they looked at many different hazards like drought and fires and floods and heat waves, and then they combined that into an aggregate hazard map. And you can see in this aggregate hazard map from climate change is that parts of Australia and those areas north of Australia are particularly at risk from increased climate change. So this is likely to drive significant changes in risk associated with agriculture and land use. And this is what we call the burning embers diagrams, or the risk diagrams associated with sort of those activities coming out of the recent IPCC special report on land use and climate change. And the important ones, I think, here is that essentially what this shows is it's color-coded, so going from white to yellow to orange to red to purple just is an increase in risk. So purple is essentially an irreversible and unmanageable risk. And what this analysis shows, drawing on huge amounts of different data and literature, is that we're currently sitting around about just over 1 degree. So we're, for dryland water scarcity, we're already in the yellow zone where there's some risk. Once we get to about 3 degrees, on a global basis, we're starting to get to unmanageable and irreversible. Soil erosion, not quite as bad in the extreme cases, but nevertheless increased risks of soil erosion, increased risks of vegetation loss, increased risks of fire damage, increased risks of tropical crop decline, and increased risks of food supply instabilities at a global level, and those cutting into irreversible and unmanageable at around about 2 degrees. So we can sort of aggregate those risks. This is done at a global level, but we can do that for Australia as well. So just a couple of slides to finish off is that how, as a sort of a decision maker, you can think about the future climates. So this is a sort of just a structured way of thinking about this, put together by Peter Heyman from South Australia and Udo Nijumolu, also from South Australia. And they sort of frame this as modelling the future, visiting the future, remembering the future, and preparing for the future. And just a really quick sort of comment on this. So looking at something like what they call remembering the future is using temporal analogues. So learning from past droughts, so saying, okay, well, the worst drought we experienced was, say, the Federation drought going back 120 years. And this is what caused it, this is how bad it was, and this is what we did about it, and this is what we've learned to manage a drought of that sort of degree of severity. So it's looking backwards, the sort of thing that I did in the first half of the talk. Then there's the opportunity to what they call visit the future. So that's using a spatial analogue to actually understand how to manage conditions that may occur in the future. So for example, if the projections are for warmer and drier conditions in southern Australia, you could look for a place which currently has those sorts of temperature and rainfall conditions that you expect in the future, and you can actually go and visit those places, learn how farmers manage those risks and what sort of systems they can use, what sort of things don't work in those circumstances, and that can inform your decisions both now and in the future. So it's visiting the future. You can also model the future, which is using climate trend analysis, which I've done a bit in this talk, and climate projections from global climate models and things like that, and use that to inform systems analysis like computer models of farming systems to model what might happen under climate change. And lastly, it's what they call preparing for the future, which is developing adaptation technologies and management approaches and strategic approaches building adaptive capacity and adoption systems, so how to move information and technologies around the farming systems, around the farming industry, so that you're actually able to do stuff when that future arises. So just the last couple of slides is that on the carbon budget and the urgency for action here. What we see when we look at the carbon dioxide and temperature relationship is that there's a strong, almost linear relationship between accumulated carbon dioxide in our atmosphere and global temperature. So if we aggregate all of the past carbon dioxide emissions that we've made as a species and translate that to global temperature, they're almost a one-to-one relationship. And so what that means is that we can actually say then, well, if we've got, say, a goal of keeping temperature down to 1.5 degrees, then you can calculate pretty much exactly how much greenhouse gases, how much carbon dioxide we can emit and still stay below 1.5 degrees. And we can take into account things like how much warming is already committed. So if, even if we stop greenhouse gas emissions right today, we still are going to have warming across the globe from committed warming from past greenhouse gas emissions. We can take into account non-carbon dioxide gases like methane, which is a big one from agriculture, and feedbacks from things like permafrost. So as permafrost melts, it can emit greenhouse gases. So for a 50% chance of keeping temperatures below 1.5 degrees, we can only emit about another 480 gigatons more carbon dioxide. And so if you think back to that first slide where we're producing almost 40 gigatons of carbon dioxide, that tells you how many years you've got under your belt. And at the moment, at current rates of emissions, we can only keep on emitting for about another 9 years at current rates and then go cold turkey and keep temperatures down to 1.5 degrees. Now, of course, we don't want to go cold turkey because that's be incredibly disruptive. So if all of this disruption in the last year was associated with a 7% reduction in greenhouse emissions, imagine what it would be like going to 100% reduction. We're not going to go there. So what we need to do is have a much longer, slower glide path down to net zero, and rather than a cold turkey thing. But the problem is the longer we leave reducing our emissions, the sharper and harder the reduction in emissions has to be consistent with any given temperature goal that we have. And unfortunately, we've known about this for a long time, but we haven't acted on it. We've still kept on increasing our greenhouse gas emissions. And that means we're facing increased risk, both associated with the climate changes themselves, reductions in water and increased extreme events, etc., but also increased risk associated with emission reduction. So the harder and faster we have to reduce emissions, the more riskier and more costly it's going to be. So quick action is good action in this circumstance, just like it was with the coronavirus. So a real quick summary. The climate is already changing here in Australia and globally. It's changing in ways which are entirely consistent with our scientific understanding of what should happen. More change is almost certain whilst we keep our foot on the greenhouse gas emissions pedal. So we need to take that foot off the pedal. The key climate variables affecting agriculture will be affected. So things like rainfall, temperature, vapor pressure deficit, etc. And that's affecting not just the averages, but also the extremes. And that's particularly important for agriculture. We can say, a priori, that these changes will make agriculture in Australia even more challenging than it has been in the past. We all know that Australia's a difficult place in many circumstances for doing agriculture, and that's just going to become more difficult in the future. Now, that's not a thing to throw your hands up in the air about and saying it's all too hard. That's a thing to say, okay, what is going to change and how am I going to manage it? So what strategic decisions can I make? What capacity do I have to build that is going to allow me to be profitable and sustainable in a changed climate? And it's really important, the last point is that I think we can address these challenges together. This is not something that the farming community has to face by itself. It's not something that just government policy is going to solve. And it's not something that the research community can do everything about. But together, we can actually devise approaches which will not only make agriculture and food security better in Australia, but we can do that in a sustainable way, which actually gives really good livelihoods and makes us all proud for the things we can do. Thank you very much.
Thank you, Mark. That's extraordinary. Every time I see it, it scares the living out of me. I'm getting feedback from someone. I don't know. Who knows? Just always disturbing when one hears one's own voice. Look, thank you very, very much, Mark. We've got about 10 minutes for questions. We've got several that have already come through on Slido. Mark, I wonder if you could turn your volume down a little bit. Is that? I wonder if that's what's causing the problem.
Well, I can.
Does that? Well, maybe that doesn't help. No, that does help. I don't know. Anywho, we have these questions coming through. If you have other questions, do shoot them through. And look, guys, I know that's an awful lot to take in, and even for someone like me who's reasonably familiar with the subject matter, it is an awful lot. And and we asked Mark to give it. We don't expect you to walk away from even this entire fellowship program with a really crisp, detailed understanding of the science. We don't expect that. Really what these are about is introducing you and to give you an overview and to enable you to ask questions, and we'll help you to find those. If there are things you don't understand, whether we can attend to them now or later, we will. We'll help you to understand as best we can what's going on. Okay, Mark, we have some questions for you coming through on Slido. Okay. So there was a question about whether COVID-19 had somehow slowed down our current trajectory. I think you sort of addressed that, didn't you? Yeah, that it's a blip. Yeah. So it's a blip. And this has been the case in the past, where the last financial crisis, emissions or pollution levels wound down, and then they wound way back up again when the recovery happened. And the key thing there is that, what that's showing is that our economy, the growth in our economy, is still tied to growth in emissions, and that's the thing we have to break.
Yeah. So I think I'd actually take a positive out of this, Corey, and I'd actually say that what COVID has shown is that we can actually act really quickly. Yeah. We can act incredibly comprehensively, even where it's actually been not in the interests of individuals, because individuals are prepared to take a sacrifice for the greater good. And I think it's actually shown that governments which take notice of science and evidence base actually tend to make much better decisions and fare much better politically than those who don't.
Mm. Okay, we may not get to all of these questions now, but we will get around to them, and ask them again if you don't get answers today. There's a question about whether beef and dairy farmers better manage soil, whether that negates their methane emissions. Mark, you're welcome to make comment on that, but we will have several presentations that address that.
Yeah,
so
a really
for those.
Yeah, a really quick comment is that yes, it's quite possible to do offsetting in that way, but important to think that there are limits to how much soil carbon you can produce, increase. There are limits to how much biomass increase you can have on a given hectare of land, and so yes, you can offset. And some farmers like John and Rob and I up in Murrum Bateman sort of area of New South Wales, they're currently offsetting about 11 times more than the greenhouse gas emissions they're producing on farm. That's both from their fine wool sheep plus diesel to run their vehicles, etc. And so it is possible to offset, but it is not a permanent solution. Whilst we produce greenhouse gases like methane from ruminants, you have to just think of this as a temporary solution.
Indeed, and Mark Wootton will address that very issue in about an hour. There's a lot of questions. Are you hopeful, Mark?
I'm hopeful that we will avoid the worst case scenarios, and I'm actually an inherent optimist. But the reality is that we're not going to get out of this scot-free. As I showed you, we've already had significant impacts of climate change in agriculture. a recent ABARES study of broadacre agriculture indicated that about a 22% reduction in profitability across Australian broadacre agriculture due to climate change already. And so what they did was they teased out the signal from improved management and technology, you know, improved breeds, improved water use, and from the climate signal. And so what actually turns out is that the increases in improvements in management essentially just offset the negatives of climate change. And when you take out that management improvement, you're left with this very negative climate change signal. And if that's 22% down, and we're only at 1.1 degree, you know, we need to think very, you know, concernedly about what it might be under 2 degrees or 3 degrees. And so I think, yes, somewhat hopeful, but also somewhat concerned.
Yeah. Can you explain the difference between sequestration and mitigation, or sequestration and carbon emissions reduction? And there's a follow-up question which goes global. Someone asks, Sophia asks, I saw a graph that shows our global carbon budget is consumed mostly by China, USA, India, and the EU. Are we able to sequester carbon being emitted by our neighbours, or does the CO2 concentrate over the area where it comes from?
Yeah. Carbon dioxide is what we call a well-mixed gas. So because it lasts for so long, it gets distributed everywhere eventually. And so, you know, a kilo of carbon dioxide, which is released in Beijing, eventually will end up at the South Pole, sort of thing. At the moment, we haven't got the trading systems that allow us to trade in a formal way across borders. We can do that in an informal way. So you can buy carbon offsets for, you know, Colombian rainforests, etc. But it's not part of an agreed sort of system. And that's one of the big issues being dealt with under the Paris Agreement that they haven't quite landed on in terms of the negotiations. So yes, it could be, and economically, if you talk to the economists, having an open and transparent and accountable trading system is actually the way to find the most cost-effective way of reducing net emissions. The previous part, or the other question, was emission reduction versus sequestration. So emission reduction is simply, if you think of below the line and above the line. So if you're producing a greenhouse gas emission, you're above the line. So, you know, when you drive your car, you'll be producing carbon dioxide and nitrous oxide, etc. And by having a more efficient car, you produce less emissions above the line. Whereas sequestration is about below the line. So it's actually about taking greenhouse gas emissions out of the atmosphere, for example, like carbon dioxide. And so they're quite different processes and ideas. And usually the first thing you try to do in most systems is you actually try to reduce the causal factor. So, you know, move to a more efficient car, you know, that type of thing. So you try to reduce the emissions rather than try to clean up afterwards.
Thanks, Mark. And we can come back to those if anything's not clear. Okay, so technical question. I've seen data that shows the temperature rise precedes the rise in CO2. Can we still say CO2 causes the warming? P.S. I'm still very concerned about climate change.
Yeah, so if we look over ice ages and the records of ice ages, is that what happens is that those ice ages in the last million years are essentially triggered by changes in the distance between the sun and the earth. And so when we're closer to the sun, we're warmer, and vice versa. And these happen over roughly 100,000 year period. It's called the Milankovitch cycle, and it's well understood and well known in the astronomical community. So it can be very precisely calculated. And what happens is that those temperatures changes, you know, with the amount of radiation we receive, obviously translates to temperature change. But the temperature change we see in an ice age or an interglacial is far, far greater than would be explained simply by the amount of radiation we receive or don't receive from the sun alone. And so what is really important is that those small temperature changes associated with the astronomical variation then trigger feedbacks in the Earth system that then influence things like the carbon dioxide and methane concentrations in the atmosphere. And it's those feedbacks through greenhouse gases which drive us down into a glaciation or drive us up into an interglacial. So it's the feedback, it's the interaction between the astronomical and the biological and physical systems on Earth that matter. So anyone who tries to separate those out is doing something really dopey, because you can't separate them out. They're actually an interaction. The changes in temperature and ice age things are an interaction between all of these different factors.
Thank you for that. I know you're a very busy man. Can we ask you 2 more questions?
Of course. No, like, I'm fine. You go
Good
for
on
it.
you. Thank you very much. Well, one question is, well, this person says, I get depressed. Do you? And they have a follow-up question. Is changing albedo factored into your predictions? And can you explain what albedo is?
Okay, so I'll do with the easy bit.
Yep.
Albedo is essentially just the reflectance of light. So the clouds in the picture behind me, they're very reflective, so they have a high albedo. And obviously, if you've got a surface which is very reflective, it tends to stay cool. If those clouds were black, if they were black soot, they'd be absorbing all that light and they'd be warming up. And this is really important in things like if you're thinking about the Arctic. So if you've got the Arctic around the North Pole and it's covered by ice, it reflects a lot of the ice and it stays cool and it doesn't melt the ice. But when it starts to warm and that ice starts to melt, even a bit of water on top of the ice significantly increases the absorption of the infrared type bands, the sort of heat in the sun's rays. But if you've got dark water, that significantly increases the amount of absorption. So when you have that, what that means is that a little bit of warming generates more warming and it starts to have a feedback. So you end up with changes in albedo, generate big changes in land systems or ice-based systems, which tend to then feed back to more change. So you get into a rapid change circumstance. And in terms of depression, of course, I'm not a psychologist and I can't speak for how people should deal with this. But my view is that we approach this from a point of view, we have a deep understanding of what is going on here and what we can do about it. Not complete, but a deep understanding. And sitting in that is the knowledge that is available that we could actually take a different pathway, which will lead to a much better circumstance where we can maintain things like agriculture and food systems, where we can maintain livelihoods and economic prosperity, etc., but without climate change. And we know how to do this. And that's the frustrating part. So I get frustrated but not depressed because there is hope, there is the knowledge that's needed, but we're just not doing it at the moment. And that's largely a question of politics.
And we will talk about that. And by the way, folks, if your question is not asked, if I don't get to your question, don't relay it to Mark now. I am recording them all, so and they will get answered by the end of the course. A couple more, just quickies. So that, given that some of the modelling that you showed there is conservative, that is to say that it's probably underestimating the pace of climate change and the impacts. How do, and again, this we'll cover this time and time again, guys. How do we communicate that message truthfully and honestly without appearing alarmist? Or how would you?
Yeah. So what I try to do is give people an understanding of what's actually going on, the processes that actually are driving particular changes, and then for them to be able to translate their own experience and understanding to that. And that way, it's not just about information that comes from me. It's actually about information that comes from both of us, the people who are engaged in that conversation. And so what that does is try to build up both understanding and trust associated with what's going on here. And I think that's really important because there's lots and lots of things going on in our society associated with social media, which are actually breaking down trust. In fact, often they're designed to break down trust. And and isolate people within particular knowledge bubbles or perspective bubbles. And I think that's a really dangerous thing. We actually are in a point in our evolution as you know, human beings in our society, where we actually need to be building bridges, where we need to be building trust, and we need to be building understanding of different perspectives. And so for me, my role here is to act as a bridge, act as a broker, provide that understanding, provide that sense making of science. And to do that, I need to know something about the business that I'm dealing with. In agriculture, I need to know something about agriculture to be able to do that sensibly. Similarly, within politics or urban systems or whatever that I deal with. And so for me, that puts a responsibility on me, not just to know about the climate sciencey side of things, but to know about something about the systems that I'm talking with people about.
Thanks, Mark. We're due to go to a break, but I just want a quick one from you. Several people have asked this. What do you see agriculture's role in all of this as a solution?
Look, I mean, it's complex because agriculture is part of the problem as well as being part of this potential solution. So when we look at agriculture, roughly speaking, a quarter of the greenhouse gases across the globe have come from agriculture directly or directly and indirectly. If we expand that to include the food system, it's closer to a third, like 29%. That's the number coming from the recent IPCC report. So to say that agriculture is not part of the problem is naive and misleading, in fact. So for me, the question is, okay, how do we acknowledge that in the first instance? So acknowledgement is the first hurdle you've got to do. And to acknowledge, you have to have good information and you have to have trust in that information. Secondly, we need to be developing good solutions. And unfortunately, we've been investing in those solutions for how agriculture can be part of the solution. But obviously, in many agricultural systems, there are opportunities to increase the carbon stocks underground and above ground in systems in ways which are still consistent with profitable agriculture. But there's ways in which you can do that which are not consistent with profitable agriculture. You can trash your system by focusing too much on one thing or the other. So for me, the question here is about not thinking that agriculture in the short term can go to zero, but how can it shave off those greenhouse gas emissions from right across the value chain that demonstrate progress, which build understanding and trust in the right through our society. We're all consumers of agriculture, we all eat, but at the same time, starting to build respect for the decisions that farmers have to make as business makers. And so one of the key things there is changing the policy and political discussions to be ones which actually acknowledge the challenge and support the change rather than doing the opposite. And unfortunately, at the moment, we have a lot of discussions which actually prevent people from talking with each other because of sort of political barriers, ideological barriers, and that prevents solutions being transferred between people. And we need those solutions to be transferred and discussed and compared, and the good ones, given airspace, and the bad ones put aside for the moment.
That's very powerful thinking, and I really like that framing of, okay, we didn't know in the past what we know now, and rather than feeling blamed, see it as a problem. How do we, not just farmers, how do we deal with this problem? What are the solutions, and how can we practically implement them at different levels? Mark, thank you so much. And folks, I know we've gone a little bit over time and you're due for a break, but I felt that was really important, and I hope you agree that Mark's presentation was fantastic. It is recorded. You can go back and look at it again, pause on graphs to digest them and understand them. If you have questions keep asking questions. If they don't get answered now, they will be answered at some point. And we can make resources available that can help you to understand these things better, including Mark's own work too. So we continue to work with Mark, or Mark very generously continues to help us. So he's not going anywhere, but he's a very busy man. Mark, thank you so much again for your time. We're really, truly grateful. Thank you for the inspiration too. It's a hard thing to communicate. Folks, we're going to go to
just letting you know, Corey, just really quickly, I'll send down the PDF of those slides so you have that available as well.
Yeah.
And as always, like I'm really happy to talk about this. Incredibly supportive of Farmers for Climate Action because you're really changing the conversations for the better in Australia, I think. And I'm happy to field questions if you send them through to me by email as well.
Thank you, Mark. And a lot of really good feedback coming back from everyone thanking you.